Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's biweekly contest, count number of possible root nodes. The problem is bit tricky, but I am very sure that if you stick till the end, you would be able to understand all aspect of this problem and you would be able to code it yourself as well. So with that, let's start. The problem states that Alice has an unrated tree n and we are given the edges of the tree, right? Notice that we are only given the edges, we are not given the root of the tree. So Alice has a tree, we are given the edges. Now Alice wants Bob to find the root of the tree and she will allow Bob to make several guesses about the tree. Now Bob, like what does a guess look like? A guess would look like Bob will select two distinct integers u and v such that u and v is already an edge of the tree. Okay, so it is one of these n minus 1 edges of the tree, and Alice will tell Bob whether u is a parent of v or not, right? So Bob is trying to guess the tree, or in other words, Bob is trying to guess the root of the tree because we already know edges. Bob is trying to guess the root of the tree, and for that he's asking queries with u comma v where he's asking Alice that whether u is a parent of v or not, and Alice told Bob that whether it is correct, whether the query that is asked is correct or not. Now, we are given the guesses that Bob makes. So, Bob makes some guesses. We are given all those uj, vj guesses. Now, Alice will not reply to each of these guesses independently. Alice will say, okay, out of all the guesses Bob makes, at least k of these guesses are true. Okay, notice that Alice is not saying that exactly k guesses are true. She is saying Bob that okay, out of all the guesses, at least k of them are true. Now we are given these edges, we are given these guesses, and we are given k, and we need to return the number of possible nodes that can be the root of the Alice's tree, right? And if there is no such tree, then we have to return zero, right? So let's take an example. Let's say these are the edges, and these are the guesses that Bob makes, and Alice finally answered that out of these four guesses, three of the guesses are true, right? Uh, or at least three of the guesses are true. All the fours can be true, but at least three are true. Now we need to return how many roots are possible, or like which all roots can be the root of the Alice's tree. So let's say we try with 0 first. We root the tree at 0. Now if we root the tree at 0, the tree would look something like this. So notice that this tree we have formed with these edges that we have given, right? 0, 1, 1, 2, 1, 3, and 4, 2. Now let's see which of these guesses are true. So 1 comma 3, we are asking Alice that whether 1 is a parent of 3 or not. So 1 is a parent of 3. This statement is true. So this guess is true. 0 comma 1, it is also true. 1 comma 0, this is not true because 1 is a child of 0 in this tree. So this is not true. And 2 comma 4 is also true. So basically 3 guesses are true for root 0. And Alice also says that at least 3 guesses are true. So basically root 0 satisfies all the conditions, and hence root 0 can be one of the possible root that Alice Alice's tree could have, right? Now, similarly, we try to root the tree at 1. Now, if you root the tree at 1, the tree would look something like this. Again, let's try to iterate over all the guesses. 1 comma 3, this is true because 1 is a parent of 3. 0 comma 1, it is true. It is not true because 0 is a children of 1. So 0 comma 1 is not true. But 1 comma 0 is true. 1 is a parent of 0. So this is true, and 2 comma 4 is also true. So again, 3 guesses are correct, which satisfies what Alice says. So all the conditions satisfied. Hence, one can also be one of the possible root. Similar, you will do similar thing for 2, 3, and 4, and you will see that okay, for 2, all the three like three guesses are again correct. So 2 can also be one of the possible answers, and 3 and for 3 and 4 only two guesses are correct. So let's just take one of the example. Let's say you root the tree at 3. This would be the tree. Now 1 comma 3, you will see 1 comma 3 is not true because 1 is not a parent of 3, so this is not true. 0 comma 1, it is also not true because 1 is a parent of 0. 1 comma 0 is true, right? And 2 comma 4 is also true, so only two of them are true, but Alice says that at least 3 is true. So it means definitely 3 is not the root of the Alice's tree, and that therefore we reject 3, root 3 and root 4. So what we found out that only 0, 1 or 2 can be the possible root of the Alice's tree, and hence the answer is 3. Like there are 3 possible roots that Alice's tree can have. So hope the problem statement is clear. Now what is the brute force solution? The brute force solution should look exactly similar to the given explanation in the problem statement. So we will just simulate whatever we have been given. So what we will do, we will try to find every tree. We will try to root the tree at every node. We will get all the entries. Now for each tree we will figure out which all guesses are true, and if number of guesses which are true is greater than equals to k, it means that can be one of the possible answer, right? So what would be the time complexity of that approach? The time complexity of that approach would be, for each, first of all we are making all the trees, right? So making all the trees would require order n square time, right? Where n is the number of nodes. Now for each tree we are iterating over the guesses, all the guesses. For 0, like for the tree which is rooted at 0, we are iterating over all the guesses. Then for 1 we are again iterating over all the guesses, right? So that would require order n into g time, because where g is the length of this guesses array. So n square time to build all the trees, and then order n into g time to find out the correct guesses for each of these nodes. So the time complexity of the overall time complexity would be n square plus n into z, which will not pass because n square itself is very huge, and n into g itself is also huge because guesses is also 10 to the power 5. So that solution would not work for sure. We have to optimize it. Now notice that we can't really optimize the brute force solution itself, the current brute force solution that we discussed, because we the brute force solution depends on we need to make every tree. So n square is something we can't avoid because that's what the base of the current solution is. So because we can't avoid n square, or for that matter we can't avoid n into g as well, because for each of these tree we are iterating over all the guesses. That is our core algorithm. So removing n square or n into g is very tough in that particular solution. So now what else? So let's try to reverse this strategy. Instead of, notice that we don't really need to know which of all these guesses are true. We just need to know count of correct guesses, right? So we don't need to know that 1 comma 3 is good for 0 or 1 or 2 or 3 or 4. So that's where what we can do, we can get rid of this list. Instead we are okay having a count here. In other words, what we are saying is it is okay that we know how many guesses are true instead of which all guesses are true. So with that approach, we can slightly modify the pseudocode. So the pseudocode would now look something like this. What we will say that for each guess g, we will try to find the roots which are satisfying this particular guess, right? So notice that we don't need to make all the trees now. We can, like, to implement this particular piece we can apply other algorithms as well, which we'll discuss later. But let's say we apply some algorithm and this is very fast, right? Now we are able to find out all the roots which satisfy the first we satisfy a particular guess g. Now for each of the roots that is there in that roots array, we incremented our count of valid guesses. So what we are saying is which all roots, for which all roots this guess G is valid, right? So at the end of this entire iteration, we will get an array which looks something like this, right? So what we will get is, okay, for node 0, like if node 0 is the root, three guesses are valid. If node 1 is the root, three guesses are valid. Similarly, if node 2 is the root, three guesses are valid, and so on and so forth. So by doing this, after we have made this array, we can simply iterate over the array and find out which of the like how many nodes have value greater than equals to k, and that count would be our final result, right? So again, we have we have previously iterating over all the trees, and for each tree then iterating over all the guesses. Now we have reversed the loop. Like previously we are iterating over all the trees, and then inside tree we are iterating over all the guesses. So we have now reversed this loop. We are saying that, okay, we will iterate over all the guesses. Now inside this, we will we need to find which all trees, or which which all rooted trees can satisfy this guess. So previously, to iterate over all the trees, you need to, like, you can't avoid finding the trees itself, right? But now you have the liberty to implement something here, some other algorithm here. So that's where we are avoiding n into g completely. Like g is there now. Inside this, whatever algorithm we will use for finding out this and then incrementing this would be something that come here instead of the number of nodes, right? So like, hope this thought process is clear now. Let's We still need to find out how to calculate this first piece. How many roots are satisfying a particular guess? We need to find out how to calculate this, and then we also need to find out how to increment the count for each of these nodes, because again, if I iterate over all the nodes, this would be n into g, which we don't want. So these are the two problems that we need to solve now. So let's start with the first one. Let's say we need to find out a way to determine which all roots are valid for a particular guess. Okay, so how many roots satisfy a particular guess I? So as mentioned the problem, the guess is determined by u comma v, where it means that u, whether u is a parent of v or not, right? So let's assume that this is the tree, right? And this is the edge that we want to consider, u comma v. Now we need to find out how many roots satisfies this piece, or how many roots are there for which u would be a parent of v. Okay, so I would encourage you to pause the video right now and try to think of which all nodes would satisfy this condition, right? So hope you have thought about it. Now the answer is all the nodes in the subtree of u, like in this particular piece, would satisfy this guess, right? Now why? Because you can see, when you form the tree, let's say u is the root, right? So if u is the root, we will come beneath it, right? So we will, like this, if u will be the root, this you can think of like this is the root, and now we will come this way, and all these nodes will be attached to v, right? So if v will come here, then u is the parent of v, hence the statement is true. Now let's talk about any of these any of the any of the nodes in the subtree of u. So let's talk about this node. Okay, so if this node is the root, then what will happen is, like, this all will be the direct children, and then this part, this entire part would be something which is attached to this node. Or in other words, what will happen is, there would be a children u, right? And beneath u there would be this v part, like this entire v part, right? So because of this case, we can again see that U is a parent of V, right? So you can try this exercise for all the nodes in this subtree of U, and you will see that, okay, for each of these nodes, right, the condition would be satisfied. So now what exactly is the answer? The answer is all the nodes which are in the subtree of U, that would satisfy this condition. Now there is a slight uh, edge cases here which we will discuss afterwards, but for now overall this is our strategy. Like, we know all the nodes in the subtree of U would be satisfying this particular guess, right? So let's try to revisit the algorithm again. So this is what our algorithm looked like. We now able to find out the value for the first query that was unanswered before. We are saying that to find like all the roots satisfying a particular guess G would be the subtree of U, right? Subtree of U. Now, next thing is we need to iterate over all the nodes which satisfy the above condition and increment the count of valid guesses for each of these nodes. So notice that if you iterate over all these nodes, so let's assume that this subtree you can find out in order one time. Like, uh, you don't need to find out the exact roots, you just need to find out the subtree, like all the nodes of the subtree of U is a valid node. So that is just order one operation. Now this part, if you iterate over all the node of this subtree of U, then this part would be order n. And if this part would be order n, this entire thing would become order n into G again, and which we don't want. So we need to make it faster. So notice that we need to add something to each of these nodes. Now this can be possible with like this can be made faster with some range query data structure. That is very clear. So from order n, we will then transform to order log n with some range query data structure here that can help us add something to all these nodes. Now, if these nodes are random, let's say we want that range query data structure to add nodes to add one to 2, 5, 7, and 8. That's an example. So let's say these are like 2, 5, 7, and 8. So we want that, and let's say this is 10. So we want to add 1 in 2, 5, 7, 8, 10, and something else, let's say 4, right? So if we do this and ask range query data structure, that will not be able to help, because any range query data structure would help only if you are doing an operation in a continuous range L comma R, right? So then only range query data structure would help. So now what's the problem statement? The problem statement is we know we need to add something to all the roots, all the nodes of the subtree, and we want to apply some range query data structure here. So this is exactly what Euler tour would give us, right? Euler tour, if you don't know about it, there's a proper video that I recorded explaining what Euler tour is. It's nothing but a simple DFS. But how it works and why it works is something I've already explained in another video. I would link that video in the comment section or in the description, and I will also link it in the top right eye icon. You can watch that. But for now, even if you don't know about it, just assume that it is a data structure that can convert the tree into an array. Okay, so if and the property of that array, so it will convert this tree into an array, and the property of this property would be each subtree would be a subarray in this array, right? So if we talk about the subtree of U, the Euler tour array that we will be forming would be a subarray. So all these nodes would be adjacent to each other. So in other words, the array, there would be some range L to R in which only 4, 2, 5, 7, 8, and 10 will be present, right? So that's what Euler tour would give us. So now the problem is simple. We will do the Euler tour, convert that tree into a array, and from this we already know which node to look at. So we know L and R, right? And what we will do, we will just add one to this range L comma R. And adding one to a range L comma R is something which is very standard range query operation. You can use segment tree or any of the range query data structure that you know about to add one to a range, right? So after this, the complexity of this part would be log n, and this entire thing would now become g log n, which would pass the time complexity. There is no issue with that, right? And after that, we are doing we are iterating over all the nodes and finding out the count of guesses. So this is something which is also possible with range query data structure, right? In log n time. So what we are doing here is again uh, iterating over all the nodes and require where each operation require log n time. So this entire thing would now become n log n. So this will become g log n, this will become n log n, and the overall complexity would be g plus n log n, and that would pass, right? So let's just take a final example, complete example, and iterate over all these pieces together, and then we'll look at the code, right? So let's say this is our tree. This is exactly similar to the first problem statement that we had. These are the edges, and we assumed, again notice on the word assumed, we assumed that the root is 0 because this assumption is something which Euler tour of the tree would require, right? So we would assume that 0 is the root. Now from this, let's say there is a guess 1 comma 2, and we need to find out, like we need to iterate over this piece for this particular guess, right? So this 1 comma 2 says that this is u, this is v, so this is u, this is v. Now we need to add 1 to all the subtree of u, only this part, right? We don't need to add to this part because that would be subtree of v, sorry, we need to add to this entire part. We don't need to add to this part because that would be like the part that v will contain. So again, if you just visualize this in terms of this particular structure where u and v are on the same level, you will clearly see that you use subtree that we are interested in is something which contains 0 1 and 3, right? And v subtree in that level where like we will just have u and v at the same level, then v subtree would contain 2 and 4, right? So hope this makes sense. Now notice that we need to add something, and this add is possible only on a subtree, right? So this is not possible on any other structure because the Euler tour gives us an array where it only guarantees that a subarray would be a subtree, like would map to a subtree in the original tree. So that was the property. There is no other property with Euler array, Euler tour array. So we need to, like we can add something in subarray, in subtrees only, but here we need to add 1 to 0 1 and 3, right? Which is something which Euler tour will not give, because Euler tour can give that, okay, I will add something to entire subtree of u, so I will add something to this entire piece. So Euler tour will not give I will add something to this all pieces, right? So we need to model it in terms of Euler tour. So how we'll model it? Again, encourage you to pause the video and think about it. Basically, uh, we need to add to 0 1 and 3, and only operation is possible is we can add something to an entire subtree. So hope you thought about it. The statement is very similar to how we do prefix sums. So what we'll say that, okay, I will add something to this entire tree, like I will add 1 to this entire tree, right? And now I will subtract 1 from the subtree of v, right? So both the operation are something which is supported by Euler tool. Like adding 1 to the entire array is something that is supported because entire array is nothing but a subtree of 0, right? So this is supported, and then subtracting is also an addition. Like you can think subtract as an addition operation itself, and we will be subtracting from the subtree of 2. So adding to subtree of 0 and subtracting 1 from subtree of 2, and this will actually, this combined operation would give us what we want. So only 0, 1 and 3 would be incremented, right? So this, like with this operation, with this, like if given query or given guess is u comma v, where u is already a parent of v, we will not simply add 1 to subtree of v, subtree of u, because subtree of u would contain much more than what we want. Therefore we will add 1 to the entire tree and subtract 1 from the subtree of v, right? But if let's say the operation is operation is reversed, or it is 2 comma 1, right? So if it is 2 comma 1, this is u, right, and this is v, and we want to add something to the subtree of u. So this would be the subtree of u in the picture where u and v are on the same level, and this would be something which is the subtree of v in that picture. So we want to add something to subtree of u, and notice here just adding to subtree of u would help. Like there's no need to touch any other thing because subtree of u is exactly similar to what we want to add to. So if u's parent is, if u not all is not the parent of v already, then we will just simply add to subtree of u, right? So hope this makes sense. So the algorithm would be something, this part is something which would look like this. So if parent of v is u already, then we will add 1 to all the nodes of the subtree of u and subtract 1 from uh, all the nodes of the subtree of v, sorry, subtree of 0, which is the current root that we've considered. Now if parent of v is not u, it means u, we simply can add 1 to the subtree of u. That should be it, right? So this part, like this entire piece, would look something like this. We can implement this in this way. So hope this entire solution makes sense. So what we have done, like we iterate over all the guess, we then see, and then we root the tree at one any given node, for example 0 in this case. So we root the tree at any given node, perform the Euler tour and get the array, right? Now once we get this array, we iterate over all the guess, we find out which subtree we need to add to, right? So again it depends on two condition, whether the given guess is already true or it is not true for this given root, and based on that we will do either this or this, right? So after this we will get a array which contain, like where each element would contain how many guesses are true for the subtree, for the tree which is rooted at a particular node I. Now we will then just iterate over this array and find out how many values are greater than equals to k, and that would be our result, right? So if you still didn't get it, I would encourage you to rewind the video and watch specific section. I would mark the starting point of specific sections in the video description. You can go through that. uh, for now I would encourage you to code this entire solution yourself. If you don't know about Euler tour, again go back to the previous video and understand what Euler tour is, or you can just simply copy paste the code of Euler tour from any sources and use that as a black box. I would strongly encourage you to code this entire solution yourself. uh, to get better understanding of this entire solution. Otherwise, you will not be able to apply this solution yourself in any other problem. Okay, so hope you have tried to at least code the solution. Let's look at the code that I submitted in the contest. So this we are using segment tree for the range queries as a range query data structure, right? So we have majorly two operation here: query and range addition. Query will just give us the value of a particular index, and range addition would just add value to the range x comma y. That's it. So basically, query would be helpful in getting this particular value, and range addition would be helpful in performing these kind of operations, right? So, and this is the Euler tour. Like this basically just fills in left, right, current, parent array, right? Now we cleared everything, and then we initialized all these vectors. We iterated over all the edges and built out the graph. Like we just said that okay, what all this is simply nothing but building the adjacency list. Now after this we did Euler tour code we'll look at afterwards, but we did Euler tour, and which will populate the left, right, and current parent vectors. So left will contain the uh, left point or left starting point of a subtree. So left I would be the starting index of a subtree rooted at I, like of a subtree I. So for example, we know that any subtree would be a range L comma R. So left I would be this L, and right I would be this R for subtree I, right? So that's what left and right contains. Now after this we build a segment tree, initialized everything with 0, and for each guess we are checking whether the statement is already true or not. So if it is not true, so basically we are checking these two conditions. So if the statement is not true, it means we can simply add 1 to left, like to L comma R, basically subtree of U. If the statement is already true, we need to add 1 to the entire tree, and we have initially rooted the tree at 0, so we add 1 to the entire tree, and if not, we will add 1 to sorry, we add 1 to the entire tree and then subtract 1 from the subtree of v, right? That's what the logic was. Now once this is done, we will iterate over all the nodes, figure out which one of them is the value is greater than k, and we'll count those and return that as an answer, right? Now let's look at the Euler tool code. This is we have mentioned, like this is something but a DFS, simple DFS. We are just marking start right and left while starting the function for a particular source and ending the function for a particular source. So we mark the starting point as this count, and ending point at the count where we are leaving this function. Now inside this we simply iterate over all the childrens, and whenever we receive a valid children we incremented the count and visit that particular children, right? So hope this entire solution makes sense. If you have any doubts in this problem, please post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.